We'll start in okay. Assalamu alaikum, everyone. Good evening. So today we're going to continue our series on selected topics on radiation physics. And we're still focusing on photon interactions. The last two lectures, we actually spent it in describing photon interactions, photo effect, Compton, Rayleigh, pair production, triplet production, and photonuclear disintegrations. And really what is relevant in our energy ranges usually in medical physics are photo effect, Compton, Rayleigh, and pair production. Triplet production is a special case of pair production where it's a pair production interaction that happens with an orbital electron, not with the nucleus. And it has a very low cross-section compared to the nuclear pair production. That's why we usually either we ignore it or neglect it, or sometimes in the data of cross-sections, they combine both the nuclear and the triplet pair production cross-sections together. But in general, the triplet pair production does not exceed 10% of the total cross-section of pair production. So today we want to take this topic further, and we want to talk about okay, is it monitor, is it by now, or can you see the
Yes,
presentation?
yes. Yes, we can see
Okay.
it.
Okay. So we want to take this further. All what we have discussed so far was actually the atomic cross sections of photon interactions. So today we want to take this further to talk about mass attenuation coefficients. We'll talk also about the mass energy transfer coefficients, mass energy absorption coefficients, and linear attenuation coefficients. So this is the summary of these photon interactions, photoelectric effect, and the dependence of the atomic cross section. It depends on Z to the power 4. Z is the atomic number, and it's inversely proportional to the energy to the power 3, although at higher energies, this proportionality becomes 1 over h mu. And the important quantity we talked about is the energy transfer. How much energy is transferred to charged particles. So in photoelectric effect, we have the photon interacts with an atom, and then the energy of the photon is given to one of the orbital electrons. Usually, it's in the tighter bound electrons. So when that electron is ejected, it will be ejected with an energy equal to the photon energy minus the binding energy of the electron. However, we know once there is a vacancy, the atomic is going to undergo atomic relaxation processes where we have transitions from higher electrons in higher orbits to fill this vacancy. And in that process, we can get either characteristic X-rays or we are going to get Auger electrons. So if we want to look at the energy transfer to charged particles, we need to consider the photoelectron, that's the initial electron that was ejected from the atom, as well as the Auger electrons that will result from the atomic relaxation process. So in short, this is the fraction, or this is the energy given to energy transfer for photoelectric effect. It's equal to, it's the fraction, so it's relative to the photon energy, it's 1. Ideally, we want all of the photon energy to be transferred to kinetic energy of charged particles. However, we will have characteristic X-rays emitted from the atom. So part of that photon energy will be emitted back as characteristic X-rays. And the most significant shell or energy that one should consider is really what happens in the K shell. So what we do is we look at what's the probability of photo effect happening with a K shell electron, and then we have the fluorescence yield of a K shell electron. Remember, the fluorescence yield is the probability of emission of an X-ray per vacancy. And then the last thing, once there is a characteristic X-ray emitted, then we need to look at what's the mean energy of these characteristic X-rays emitted. So we have to subtract these characteristic X-ray energies from the energy transfer. And then we moved on to Rayleigh. Rayleigh, this the atomic cross-section is proportional to Z squared and inversely proportional to the energy, photon energy squared. And with Rayleigh scattering, we know that there is no energy transfer to electrons. So the photon is just scattered with the same energy at a different angle. That's why the energy transfer fraction for Rayleigh equals to 0. Compton scattering, the atomic cross-section is proportional to Z. And in general, the cross-section decreases with energy. The only exception is at very low energies, there is an increase because of the binding effects of these electrons. And the mean energy transferred to Compton electrons, this is a quantity, it's an average. So for example, if I have a 1 MeV photon, this 1 MeV, the energy transfer to the electron will depend on the scattering angle of the photon. So we need to consider all possible scattering angles and consequently calculate the energy that will be given to the electron for that particular angle. But we also need to take into consideration the probabilities of these scattering angles to occur. And when we do that, we get this nice graph. It's a sigmoidal graph. This gives me the cross-section, the energy transfer fraction. So let's go back. We have a larger graph somewhere here. Yes, this one. So it's given by this horrible equation here. That's the mean energy transfer fraction for Compton. But the solution is this sigmoidal graph. So there are anchor points. Usually this is something we memorize. At 1 MeV, the value is 0.44, meaning that if I have a 1 MeV photon, then the mean energy transfer to a Compton electron is going to be 44 keV. If I had a 10 MeV photon, then the mean energy transfer is going to be 6.84. Remember, this is the fraction. It's the kinetic energy divided by the photon energy, and so on. At 100, about almost 80% of the photon energy is transferred to kinetic energy for electrons. And at lower energies, we see that the fraction of the photon energy transferred to Compton electrons is actually small. Only about at 10 keV, or if a Compton scattering occurs, only about 2% of the photon energy is actually transferred to the electrons. This is the average quantity. And finally, for pair production, this is the dependence of the atomic cross-section with respect to the atomic number. It's proportional to Z squared. And actually, this decreases. This is a typo. It should be increases with H mu. So the cross-section increases with, let me fix this quickly. Yes, so the cross-section of pair production, it will increase with with the photon energy. Also, we mentioned that for pair production, it has a threshold. This threshold is going to be about 1.022 MeV.
Yes, sorry, sir. We can't see your slides. We are
Slides
seeing the green screen
the
or
green
the
screen.
background. Yeah, it's the background of your computer or something.
Okay, how about now? Is it
Yes.
there?
No.
Okay.
Yes. We can see it. Thanks.
So for pair production, we said that there's a cutoff energy below a threshold energy. Below that, this interaction cannot occur. And the energy transfer for the positron and electron that are produced in this interaction is going to be, or this, the energy transfer is the photon energy minus 2 MEC squared over Hp. So this is the transfer fraction. We've also mentioned that there are some effects that happen after photon interactions. So for example, vacancies will be produced in photoelectric effect, Compton scattering, triplet production. And these vacancies will be filled with orbital electrons, making transitions from higher to lower levels. And while this transition happens, we will get emission of characteristic X-rays or G electrons. Another thing that could happen is when we have a positron. So positrons are produced when we have a pair or a triplet production. So the positrons, they will interact with medium until they lose their energy. And once they lose, they will combine with an orbital electron and produce two annihilation quanta. Usually they are at roughly around 180 degrees. It's a little bit less. I think it's 179.5 degrees. So the two annihilation quanta have most commonly an energy of 0.511 MeV each and are emitted at approximately 180 degrees. But for positrons, annihilation in flight might happen. So before the positron loses all of its energy, it might actually encounter an orbital electron and annihilate with this orbital electron. This process, we call it annihilation in flight. So the total atomic cross-section is just simply is given by the cross-sections of these four interactions. Triplet is somehow it's included in the pair. And then we have the photonuclear disintegrations. These are the magnitude of the cross-sections are very small, negligible compared to these other photon interactions. So usually we say, okay, the photon interaction, the cross-section is just, the total cross-section is the sum of the cross-sections of these four interactions. These are some of the graphs of the interactions here of the cross-sections. This is for photoelectric effect. We can see that, okay, the cross-section increases with Z to the power 4 in this case. For Compton, this is Compton here. It depends on Z, the atomic cross-sections, and with energy they decrease, usually decrease, except in this low energies, and this is because of the binding effects of electrons. Because in Compton, the assumption was that electrons are free, but in reality, electrons are always bound to an atom. So when the photon energy is very low and the energy transfer to these bound electrons is not sufficient for for the electrons to leave the atom, then no interaction will occur, and this is why the cross sections they decrease here. Rayleigh, here we have these are the curves for Rayleigh, and this is in comparison to Compton. And here on this bottom here we have the cross section for pair production. So now when we look at one material, one element like carbon, here we're plotting the cross sections. This line represents for photo effect. This is Rayleigh and Compton and pair production. And then the solid line here, this is just the total, the sum of all of these cross sections. Remember, this is a log scale. It's a log scale here. And here on the right, we have the same figure, but now we're plotting the cross sections for carbon. For lead. Although these are the mass attenuation coefficients, but the atomic cross sections will have the same features. So what's the mass attenuation coefficient? The mass attenuation coefficient or the mass cross section is basically the sum of the atomic cross-sections in 1 gram of media. Imagine, for example, we have, so we now know what's the cross-section, let's say for hydrogen, for one hydrogen atom, the cross-section for all of these 4 interactions, and the total cross-section. What we need to do is to get 1 gram of hydrogen, and then we sum all of these cross-sections. The sum of these cross-sections of all hydrogen, let's say in 1 gram of hydrogen, this is what's called the mass attenuation coefficient. So the number of atoms in 1 gram, this is given by Avogadro's number divided by the atomic mass. And since A for elements is approximately equals to Z, then the power, the dependence of the atomic cross-section for mass cross-section, the dependence of the atomic number for the mass cross-section is usually lesser by 1 than that for atomic cross-section. So for example, for photo effect, we said that the atomic cross-section for photo effect is proportional to Z to the power 4. However, when we're looking at the mass cross-section, then the proportionality will be depend on the atomic number -1. So if it's here Z to the power 4, it's going to be Z to the power 2. The same thing will be, for example, for Rayleigh. Rayleigh depends, the atomic cross-section for Rayleigh depends on Z to the power 2. So when we're talking about the mass cross-section for Rayleigh, it is going to be, it's going to depend on Z only. Compton, the atomic cross-section for Compton depends on Z. So the mass attenuation for Compton is actually independent of Z. So it depends on Z to the power 3. This here is a table that summarizes all of these important cross-sections, the energy dependence, and the atomic coefficients. That's what's important, and the mass coefficients, the dependence of. And here we see for Compton, it's independent of Z. Okay, or it's, one can think of it, it depends on Z over A. So Z over A, since A roughly equals to 2Z, then it's independent of Z. The only exception to this rule is going to be hydrogen. Hydrogen, yes. So hydrogen, Z over A is equal to 1, whereas Z over A for higher elements, for high Z material, roughly equals to 0.5. So hydrogen, believe it or not, has the highest Compton mass coefficient compared to other elements. Another exception is also going to be helium-3. Helium-3, I think the Z over A is going to be equal to 0.6 something, 0.67, I think. But for higher elements, the Z over A is going to equal to 0.5. So if you go and look at some table with mass attenuation coefficients, you will going to observe that the mass attenuation coefficients for hydrogen is almost double that of, let's say, of carbon and other higher elements. It's always going to be higher. So what is then the relative interactions with? We now have these 4 interactions that we discussed. So we want to know that, so when a photon is going to interact, it will have a certain probability to interact in one of these. So suppose the photon is going to interact, there is a chance that it might undergo an interaction following one of these 4 interaction modes. So what's the relative then weights of this, or what's the probability of photon undergoing photo effect, Compton, and so on? So this could be calculated by just taking the cross-section of a given interaction divided by the total cross-section. So this is the interaction, or the relative weight of a given interaction is given by the cross-section for that particular interaction divided by the total interaction, the total cross-section. Here is an example. So if we want to consider, okay, we want to calculate what's the weight or what's the probability of the photon undergoing photo effect if the photon is going to interact, it's basically going to equal to the photo effect cross section. You can take it as the atomic cross section, the mass cross section, it does not matter as long as we're consistent. So if we take this as the atomic cross section, then we divide here by the total atomic cross section. If we're taking this as the mass cross section for photo effect, then we divide by the mass cross section mu over rho. For Compton, again, it's the same concept. The weight of Compton would equal to the cross section for Compton divided by the total cross section. So this is the graph for carbon again. These are the cross sections for photo effect, Compton, Rayleigh, and pair production. So we can then calculate what is the weight, let's say at 1 keV, or here is 2 keV. What's the weight? What's the probability of these interactions to occur? So for photoelectric effect, so here we're talking about 2. So we're going to take this value divided by the total cross section. And obviously the two curves are on top of one another. So the interaction weight is almost 100% or 1. Now, if you go to another region, let's say here at 1 MeV, so 1 MeV, we need to look at the Compton multiplied by, divided by the total cross section. And again, we see both curves are roughly the same. This is why at 1 MeV, the weight of Compton is 100%. What does this mean? It means that if I have a 1 MeV photon, and this photon is going to interact with matter, then the probability of this interaction to be Compton is almost 100%. We're very certain almost that interaction is going to be Compton. If we come to somewhere here, let's say at this region here, then okay, the interactions, the cross sections of photo effect of Compton, they're lower or lesser than the total cross section. This is why the weight of these interactions for Compton, this curve and the photo effect, they are not 100, but they are at a smaller number. And again, we can apply the same concept for pair production. Notice that below 1.0225, the weight for pair production is 0, and then this weight will start to increase because the cross section for pair production, then it will start to increase and becomes the dominant interaction at higher energies there. Here I'm plotting 2 points. One, this in red, this is basically the energy at which the photo effect and Compton cross sections are equal to one another. And in this region, this blue line or blue dot, this also represents the energy at which the cross section for Compton and pair production is equal to one another. Lower than this point, lower than this energy, we will see that photo effect dominates. It's the dominant interaction. And this on the weights, you see, it goes like this, it becomes 100%. In between these 2 points, between these 2 energies, Compton becomes dominant. So Compton, beyond this red point, the weight, interaction weight, starts to increase until it reaches 100, and then starts to decrease again at this energy here. And on the right of this energy, higher than this energy, we see that the dominant interaction is going to be pair production. This is again the same concept. This is now for lead. Again, we have these 2 points here, or we're representing the energy at which Compton and photo effect are equal to one another. And this energy here represents where Compton and pair production are equal to one another. In fact, this is the same, these are the interaction weights, but now drawn for 8 different elements. So we have carbon, aluminum, copper, molybdenum, tin, tungsten, lead, and uranium. And these are the weights for each of these interactions, or each of these elements. We can do this exercise. So we can, Ali, for example, can start to say, okay, I'm going to record or collect these energies at which photo effect and Compton are equal to one another. I will do this for all elements from Z equals to 1 all the way to 92, 92 being uranium. So he's collecting, okay, for carbon, this is the energy, aluminum, this is the energy, and so on. And then we have another guy, so Saleh, for example, he could start to say, okay, I'm going to do the same exercise, but I'm going to do it for energies where Compton and pair production are equal to one another. So now he's registering, collecting these energies as a function of atomic number. So, and then we come up with this graph. So now we plot here the energies, and then for a given element, so this is a carbon, Z equals to 6. I will ask Ali, at which energy photo effect and Compton are equal to one another. Then we'll put a point here. And then for Saleh, we'll ask him, okay, what is the energy at which Compton and pair production are equal to one another? We will decide, okay, this is the energy. So we'll put a point here. And then we will repeat the same process, put all of these points to get this line. So this line represents the energies at which photo effect and Compton cross sections are equal to one another. And then this line or this curve here represents the curve at which photo effect, Compton and pair production are equal to one another. So we get this like a curtain curve. And as you can see from the figure, now we have this space is divided into 3 regions. Anything below this line, we would say photo effect is going to be the dominant interaction. Anything in between these 2 lines, we'll say Compton is going to be the dominant interaction, and anything above this line here, we say pair production is going to be the dominant interaction. So why this curve is important? We can, for example, quickly estimate, okay, or determine. Let's say if we have an exercise, we have a question, we have a material of, let's say, 10 Z equals to 50, and we have a photon that its energy is 100 keV. So the question we're going to ask, what is the dominant interaction? So all interactions can happen except for pair production, obviously. But what is the dominant? What's the most likely interaction to happen? So we'll go to this curve here, and we will look at, so the photon energy is 100 keV. It's here. And then we are 10 is going to be 50. So our point is going to be here. So this point is in this region where photo effect is dominant. So immediately we'll say, okay, in this, for 100 keV, in 10, the dominant interaction is photo effect. It doesn't mean it's the only interaction. It's the dominant. It's the most likely to happen, but does not necessarily mean it is the dominant. If we look at this, a typical question that usually I've seen this in many MCQs on board exams. For example, the dominant interaction of the tissue for, let's say, for 100 keV or 500 keV. So tissue is called carbon. So with tissue, usually say, okay, carbon is a good representation of tissue. 6 Z or maybe about 7, I think the effective or but anyway, it has a low Z there for carbon. And if we're talking about the 100 keV, so our point is going to be here. So here, immediately we'll say, okay, the dominant interaction is actually Compton. So in diagnostic radiology, in tissue, the dominant interaction is going to be Compton. Actually, the point is here, somewhere here. So only I think when we go to very low energies like mammography, the dominant interaction is going to be probably photoeffect. And this is why scattering is a big problem in diagnostic imaging. To get the image, Compton is actually ruins, the image. And there are some solutions, for example, using a grid and so on, just to eliminate, to remove those Compton scattered photons from reaching the film or the detector. It's also, this curve, it's very good, could be used, for example, to quickly estimate things, as we'll go through maybe an example maybe today or next time. So anyway, this is the very famous curtain graph, and I hope now you understand how this graph was actually constructed, how it is made. It came from these things. Or you can take the plotting just the cross sections graphs. We just pick up the energies at which photo effect Compton and pair production and Compton. We pick up these two energies, but we need to do it for all elements Z. So the energy transfer. Now we have a photon. This is an important topic. Now we have a photon interacting in, let's say, a medium. The question is, what is the energy transfer to charged particles? Because that is the first step in order to calculate the dose later on. What's the dose absorbed in medium? So the energy transfer is basically given as the sum of the product of the mean energy transferred for each possible interaction and its relative interaction rate. So a photon, when it interacts, it can undergo photo effect with a given probability. It can go for Compton with a given probability, Rayleigh with a given probability, and then pair production with a given probability. And for each of these interactions, the energy transfer to charged particle is different. And this is what summarizes the energy transfer. So you got photo effect for Compton, for Rayleigh, for Compton, and for pair production. So to calculate what is the energy transfer for a given photon, we need to first calculate or get what's the interaction weight, what's the probability of that interaction to happen, and then we multiply it by the energy transfer for that particular interaction. So this is basically an average quantity of the energy transfer for average over the four possible interactions. From there, we can then calculate an important quantity in dosimetry, which is the mass energy transfer coefficient. So the mass energy transfer coefficient is equal to the mass attenuation coefficient multiplied by that energy transfer divided by the photon energy. Usually in books, in data books, you will see, for example, data for the mass transfer coefficient. This is basically given by the mass attenuation coefficient multiplied by the energy transfer over photon energy, or this is sometimes it's called the energy transfer fraction. Now, these charged particles, when they are produced, so now we have the photon interacting with matter, and energy is transferred to charged particles. Charged particles, they will undergo some interactions. We will deal with this in the future, inshallah. Charged particles, when they interact, they either can ionize matter, these are called collisional interactions, or they can actually emit X-rays. These are called radiative interactions or Brahmi-Sharad. So now we want to, or this concept, the mean radiation fraction, is basically defined as the mean fraction of energy that is transferred through photon interactions from photons to energetic charged particles and subsequently lost through various radiation processes as the charged particles move through the medium. So the photon, think of it in this way: the photon interacts, gives energy, certain energy to these charged particles, and then these charged particles will subsequently interact with medium. And while they're interacting, they are going to emit photons, either through Bremsstrahlung, we'll talk about this, or by annihilation. So anyway, the energy that was given to these charged particles was not spent in ionizing matter. Part of that energy was re-emitted back as photons. That fraction of energy that is emitted back as photons divided by the initial energy that these electrons got from the photon, that is called the mean radiation fraction. So how photons are going to lose their energy in the form of photons? One way is through Bremsstrahlung interactions. So this is something we talked about it a little bit when we dealt with the production of X-rays, but we will have a session talking about interactions of charged particles with matter. So this is one way, and this is actually the dominant way of electrons losing their energy to X-rays. Okay. Another possibility of the photons, or this actually is really specific to positrons, is that these positrons, they will undergo in-flight annihilation. So the positron obtained energy from the photon. And this positron, ideally, it should actually lose all of its energy, and at the end of its path is going to undergo annihilation. The annihilation photons, this is fine. That's not a problem for us. The problem is, what we're concerned about is we gave the positron a certain amount of energy, and we were looking at how much of that energy is going to be lost back or emitted back as photons. So if the positron just undergoes collision interactions in the medium, and after it loses all of its energy, it annihilates, then we can safely say this positron, we gave it that specific amount of energy, and all of that energy is then transferred or used in ionization or deposit those in the medium. So in this situation, then the radiation fraction is going to be 0, because all of its energy was spent in collisions. After it lost all of its energy, it went through annihilation. That's fine. That's not a problem. But there is a chance that positrons might undergo in-flight annihilation. So before they lose their energy, they might actually find an orbital electron, and then they will annihilate. They annihilate one another, emitting photons again. So the initial energy that was given to the positron was not totally or fully spent in collision interactions or in the dose. In this case, there is, yes, a radiation fraction. And the radiation fraction in this case, we look at how much energy was actually the positron had before before it went through or it underwent in-flight annihilation. That amount of energy divided by the initial energy, that will be the Bremsstrahlung fraction. So let's look at an example. So that we hope this. So now we have a photon. Okay. So this is energy. Let's put this as, for example, 10 MeV. And we know, suppose it went and did an electron, and we have a positive. Okay. And this
So
positive.
please, can you get your microphone nearer? So we can. Yeah, so that we can hear you better. Thank you.
Okay. So this positron, okay. Suppose when it had an energy of 1 MeV, what happened is we get annihilation. Okay, it can have two energies, three photons, or two photons, and so on. So what is then, how do we then assess for this? We know, for example, there was 1 MeV when the positron had undergone this in-flight annihilation. So at least the energy transfer, the radiation fraction, is going to equal to the energy that was transferred to, in this case, the energy transferred is equals to 10 minus 2 MEC squared. So this is roughly, we'll say roughly around 9 MeV. Okay, and let's assume this electron did not undergo any Brahms-Lang interaction. It went and spent all of its energy until it came to a full stop. Okay, but the positron, it actually had an in-flight annihilation at 1 MeV. So then in this case, we would say the energy transfer, or the G, sorry, but interested to look at G, the radiation fraction is going to be equal to 1, which is this MeV divided by the energy that was transferred to the charged particles, which is 9 MeV. So about 10% was lost back or as X-rays. A third possibility of radiation losses is fluorescence radiation. We know when the photon interacts, electrons are produced, and these electrons will then further ionize atoms in medium. When they ionize, they will create vacancies, and then the atoms in the medium will undergo atomic relaxation. This means that there is a chance that in this atomic relaxation process, we get X-rays emitted. So that is also a form of a radiation loss. However, the energy that is emitted in fluorescence radiation is usually much lower than the energy or photon energies emitted in Brahms-Lang or in-flight annihilation. That's why it's usually negligible. We don't really consider it at all. So if we plot this mean radiation fraction as a function of energy, here we have this plot for different elements. We see here at very low energies, low photon energies, all of the energy that is transferred to charged particles is almost going to be spent in ionizing matter or in those. However, as the photon energy increases, then the charged particles, the energy transferred to these charged particles will be higher. And this means that there is a higher chance of these charged particles to undergo Brahms-Lang interactions while they're losing their energy. And this explains why the mean radiation fraction curves, they will start to increase as the photon energy increases. So remember, the mean radiation fraction is a quantity to describe photon beams, okay? But we have to understand the process. The photon beam, first, it will interact, transfer energy to charged particles, electrons and positrons. And then when these electrons and positrons interact with the medium, there is a chance that they are going to emit photons. Okay? This is not to be confused with the radiation yield. Radiation yield is something related to charged particle interactions. It is the radiation fraction is a quantity specific for photon beams. So somehow the radiation yield is somehow hidden in all of this. And for each element, here we're showing two curves, one with a solid line and one with a thin line. So the solid line represents the radiation yield from Brahmi as well as from in-flight annihilation. So this is the total mean radiation fraction. And the thin line shows the radiation yield only from the Brahmi. And you can see that the two curves are very close to one another. This means that the in-flight, the radiation loss, or the radiation fraction, considering only in-flight annihilation, is much smaller than that lost from Brahmi. So again, here, this is why the Brahmi interactions, when we're talking about the radiation losses, is the dominant process. So for a given photon energy, the mean radiation fraction increases with absorber atomic number. We can see this from these curves. So we have carbon, aluminum, copper, and this could always be explained when we move to interactions of charged particles with matter, because the Brahmi or radiative stopping power is proportional to Z. So it will increase with Z. And then for a given atomic number, the mean radiation fraction increases with photon energy and saturates at 1 at very high photon energy. So we would expect, if we extend this plot to going to very high energies, then we would expect that these curves will all saturate at 1 at very high energies. The Brahmi fraction is the sole contributor. So this is for Brahmi, is the sole contributor for G for photon energies below 1.022. Why? Because we know at 1.002, pair production cannot happen. Therefore, we are not going to get any positrons. So any radiation, the radiation or any radiation losses at these low energies, this is due to these electrons undergoing Brahmi radiation. For photon energies greater than 1.022, pair production becomes possible. And both the mean Brahmi fraction, so things from Brahmi as well as from annihilation, both of them will contribute to the total radiation fraction. However, the mean radiation fraction from Brahmi is really the main contributor for all photon beams, for all photon energies, and exceeds a lot the whatever losses happening in flight annihilation. At photon energies greater than 10 MeV, the mean Brahmi fraction increases almost linearly. So here at 10, so this increase is almost like a linear. We expect it to go like a, however, the word linearly, I'm not sure if this is, yeah, but here this is a log scale. So one has to look at in terms of a log scale, a linear scale. Anyway. The mean flight annihilation fraction first rises rapidly with photon energies and saturates around G equals to 0.2 at photon energies equals to 20 MeV for high Z absorbers, and at photon energies around 100 MeV for low Z. What basically they're saying here is that this saturation, although we expect, theoretically that they go to 1, however, at 20 MeV, we start to see, okay, there is more like here there is a rapid increase initially for high Z material, and then the increase beyond 20 MeV becomes a little bit less than that. For low Z, still this increase is going to be fast until at 100. And then we expect it to somehow, the increase is going to be a little bit lower beyond 100 for low Z material. This is the important thing for you to, just like a figure or a number to remember, that for low Z material absorbers, typically water. Why this is important? Because we're talking about water, especially when we want to calculate the dose, for example, from chambers and so on. The mean is negligible and roughly around cobalt or in the MV range, the Bremse rank fraction is roughly around 0.3%, so 0.003. This means that in the megavoltage range, typically in our therapy, most of the energy that is given to the charged particles, most of it will be actually used in absorbed dose or ionization of matter. Only about less than for cobalt is going to be 0.3%. I think for higher MVs is going to increase that value. But let's say about 1% of that energy in the megavoltage range will be transferred back to photons. So if we're interested to know what is the absorbed dose locally in a specific region, then definitely we need to consider how much of the energies that are given to the electrons are re-emitted back as in the form of X-rays, because these X-rays will leave our region of interest and will not contribute to the dose in that region. So the energy absorbed, now this should be absorbed. Okay, typos. Well, I need to again do this and share again. So the energy absorbed is then, so we know how to calculate the energy transfer. The energy transfer is given by this equation here. The interaction weights multiplied by the transfer of each of these interactions. And then the energy absorbed, we'll just say, okay, it's equal to the energy transfer, but we need to subtract this radiation fraction from that. So in general, the energy absorption is always going to be less than the energy transfer, except at very low energies where this G fraction is almost zero. Then we'll say at very low energies, the energy absorbed is going to be equal to the energy transfer. However, for megavoltage beams and higher, the radiation fraction has a value. So the energy absorbed is always going to be less than the energy transfer. And we can then calculate what's called the mass energy absorption coefficient. This is basically, it's the mass attenuation coefficient times the energy transfer over h mu, or this product, the product of these two is basically, it's the mass transfer coefficient multiplied by 1 minus the radiation yield. The linear attenuation coefficient, this is, I think, all of us were familiar with it. I was hesitating to actually put it because I think it's general knowledge, but however, just for completeness, let's go through it very quickly. So it is actually the most important parameter used for characterizing X-ray or gamma ray penetration into absorbing media. So this is the linear attenuation coefficient. We often say, okay, if you want to characterize the beam, one way to characterize it is by specifying the energy spectrum of the beam, or another way to say, okay, this is the linear attenuation coefficient of that beam. Linear attenuation coefficient, we can think of it as a way to describe the probability per unit path length that a photon will have an interaction with the absorber. And this linear attenuation coefficient, it depends on the photon energy as well as the atomic number. All of these all of the cross sections we talked about, they have a dependency on the photon energy and on the atomic number set of the absorber. So we can calculate the linear attenuation coefficient as the mass attenuation coefficient multiplied by the density of the material. or if you like this notation, I like this notation, mu over rho, but sometimes it's confusing. People say, okay, well, it's mu, we cancel mu on with the rho with the rho. Well, this is a quantity, mu over rho. It has a specific name. It's the mass attenuation coefficient. And that's why in some textbooks, they will put this quotient as mu sub m. So if we know the mass attenuation coefficient, then we can calculate the linear attenuation coefficient by multiplying the mass attenuation coefficient by the density. So now we should be able, if we have atomic cross sections, we should be able to calculate the mass attenuation coefficients as well as the linear attenuation coefficient. So going from atomic to mass. So if we have an atomic cross section, okay, then the mass cross section equals to the atomic cross section multiplied by NA over A. And then the linear attenuation coefficient equals to mu over rho multiplied by rho, which is equal to mu NA over A multiplied by density. Okay, so if you have tables where they're listing the total atomic cross section, you can calculate immediately what is the linear or the mass attenuation coefficient, provided that you know what is the density of the material as well as what is the atomic mass. So for a small thickness, if you have a small thickness of dx, then the decrease in the intensity of a photon beam is given by this decrease is equal to minus mu x. If we have a large absorber thickness, then the intensity of the beam after traversing a thickness of x is described by the standard law of exponential attenuation. I think all of you know this law very well. So the intensity at thickness x equals to the initial intensity multiplied by e to the power minus mu x. And if we plot the attenuation law, we get this very famous curve that I think all of you are familiar with. Now, there are some characteristic thicknesses for the absorber. For example, first thing is we have this, what's called the first half value layer, or simply the half value layer. It is basically the thickness of an absorber that attenuates a narrow beam to 50% of its original intensity. So the half value layer, so if we look at this here, so if we start with this intensity and we look at this curve, then we want to know at which thickness the intensity is going to be half of its original value. This thickness is called the half value layer. And it is related to the linear attenuation coefficient by the following relationship. HBL equals to ln2 divided by the linear attenuation coefficient. So if, for example, one has, from a data book, we have the linear attenuation coefficient, and we can then calculate what is the half value layer in that medium for that particular photon beam. Another quantity that is related to, again, a characteristic of the absorber thickness is the 10th value layer. This has, its applications is more in radiation protection, but it's defined as the thickness of this absorber to attenuate the beam to 1/10 of its original intensity. If we look back here, so this is our curve, and we want to know at which thickness the intensity is 1/10 of the original intensity. That thickness is called the 10th value layer. And then we have another quantity. It's called the mean free path. It's not used as often as the HVL or the TVL. It's basically the thickness of the absorber that attenuates the narrow beam intensity to 1/8, okay, or 36.8% of its original intensity. And it's given by the mean free path is given by just the reciprocal of the linear attenuation coefficient. So if we go here, we look at this and we look at when I equals to 36.8 of its original intensity, this value is then this is then given as the mean free path. In some situations, okay, or we can think of another quantity, it's called the second half value layer, which is HVL2, is basically the thickness of the absorber that attenuates, again, a narrow beam intensity from 0.5 to 0.25. So if we look at this curve here, okay, it's not shown, but let's try to draw something. So let's remove these points. So this is 50%. Then we need to go to 0.25, which is here. So this is the line. Okay. Here, this is the second half value layer. So this is HVL2, this thickness. From here all the way to here. That is, sorry, so it's not confusing. We will erase this. So from here to here, this is HVL2. It's this thickness. So we look at which thickness we get 0.25. So the difference or the thickness requiring to attenuate the beam from 0.5 to 0.25, this is HVL2. And this is here HVL1. Okay, so we have a thickness HVL1 reducing the intensity from 0 to 0.5, and then we have an HVL2 reducing the intensity from 0.5 all the way to 0.25. This is HVL2. If we had a more energetic beam, then we are going to expect that actually there is a parameter here I did not define. So this parameter X is called the homogeneity index. So this homogeneity index is basically the ratio of HVL 1 over HVL2. So if we go to our figure here, so we can define this homogeneity index. So basically, this homogeneity index is basically equals to HVL1 divided by HVL2. Okay. So we can have, if Hx equals to 1, that means HVL1 equals to HVL2, then the beam is said to be monoenergetic. This is a monoenergetic beam. Example, for example, would be cobalt-60, beams produced by cobalt-60 or cesium-137, they're almost like monoenergetic. If this homogeneity index is not equal to 1, then the beam probably is a spectrum, is not monoenergetic. So it means that it has photons with different energies in the beam. And for each given energy, they are attenuated differently from the others. So two things could happen, is if this homogeneity index is less than 1, that means the first half value layer is smaller than the second half value layer. Then we say the beam is actually being hardened. This means that if we have a spectrum, this attenuator attenuates more the low energy photons in comparison to the high energy photons. So as the beam moves away, penetrates the medium and undergoes, let's say, 1/2 value layer, then the low energy photons will be much reduced than the high energy photons. And then we will have a different, we will need a larger thickness or a different thickness to attenuate the beam further, to reduce it to 1/2, another 1/2 of its value. So to reduce from 0.5 to 0.25, we will need a larger thickness than to reduce it from intensity from 1 or 100% to 0.5. In this case, we say that the beam is hardened. This is often if you're doing radiotherapy, and for example, you're measuring attenuation, let's say, of a block or any high Z material, looking at an X-ray beam, then you will often find that the second half value layer is actually larger than the half value layer, meaning to reduce the beam from 0.5 to 0.25, you need a more thickness than to reduce it from 1 up to 0.5. And we say that in this situation that the beam is hardened. The energy, the mean energy of the beam has actually increased. It could happen also that we get this homogeneity index to be greater than 1. This means that the first half value layer is actually higher than the second half value layer. And the beam is set, then the beam is softened, meaning that the mean energy of the beam has actually decreased. A good way to explain this phenomena is if we look at our, let's say, an attenuation curve for photons. We know we have photo effect, and then we have Compton, and then we have pair production. So here is the photon energy, and then here we have, for example, our linear attenuation coefficient. So imagine we have a beam with a spectrum that looks like this. Okay. So what we're going to see is that these photons, because the linear attenuation is high, then as the beam penetrates the medium, then what's going to happen is we're going to get the spectrum to look something like this. There is attenuation for higher energy photons, but the attenuation for lower energy photons is actually more. So if we look at the average energy of the photons, probably you will see that this was the average energy of the spectrum, and now the average energy of the beam after undergoing this attenuation has actually increased. The mean energy of the beam has increased. We could have the same situation, but now we're looking at this at the other part where we have a spectrum that looks like this. I'm exaggerating, but the point is that because this region of energy corresponds to this region here in the curve, then what we're going to end up with something like this. So there is going to be more decrease in the high energy photons compared to the lower energy photons. And again, the mean energy, so it was here, now it should become a little smaller. The mean energy of the beam. In this situation, we call it softening, and in this case, we call it hardening. You will see softening of beams if you do it for, let's say, for an 18 MV beam. 18 MV beam, if you measured attenuation of 18 MV beam, you're very likely that you're going to see that the second half value layer is actually less than the first half value layer, because the beam has softened. So I have two slides, additional slides, but let's try to look at these quantities. Okay. So the kernel is basically the kinetic energy released in matter. Let's look at this problem. Suppose I have a layer, okay, and this has a thickness of dx. And we have a beam, photon beams. We have n photons, okay, and 0 photons incident on the slab. So what we want to do is we want to calculate how much energy is being transferred in this medium. So this is what we're going to call kernel. Is basically equal to the energy transfer divided by the mass of this. So how we approach this problem? First, the first thing we need to do is we need to calculate how many photons are going to interact in this slab, this small slab. So the number we know from the change of photons after the slab is going to equal to minus mu times dx. This is the thickness dx. So this is the change. This is basically how much are left. So the number that interacted in this, or basically this is the number that are going to undergo interaction here in this slab. Then we have, this is the photon beam, okay, this has an area, this slab has an area here, area A. And it has a thickness of dx. So what we need to do is, so this is the change, this is the number that, let me get this straight. This is the attenuation, the number of photons, the change, okay, is negative. So the number that have interacted here is going to equal to, this is the number, or let's move. This is the change. This is how many photons we lost actually in this slab. So this represents the number of photons that interacted in the slab. We want to calculate the energy transfer. So for each interaction, so if we have for each interaction, we get the energy transfer. Well, let me put it in this. So the energy transfer basically equals to, we have this number of photons that interacted, and we need to multiply it by the mean energy that is going to be transferred from each of these interactions. So it's this quantity that we talked about. So the E transfer, remember, this equals to the interaction weights, the sum of the interaction weights multiplied by the energy transfer of a given interaction. So the energy that is transferred to electrons here is going to equal to the number of photons interacting multiplied by the mean energy transfer for each individual interaction. Okay. We also need to calculate the mass, because this is the definition of the kernel. So the mass, this is going to equal to the area multiplied by we're talking about the density multiplied by the volume. So the mass equals to the area multiplied by this dx multiplied by the density of the material. So what do we get from here? We get that the Kerma I'll just put K for it, equals to this energy transfer, which is dN, multiplied by something is not right. I think there is an N here. This is the N0. We need an N0. So in the equation there, because this change is related to the N0. Because from here we get dN over N0. Yeah, this is the correct equation. Minus mu dx. That is the correct equation. I need to fix my slides. Okay, so here we have this is energy equals to dN. dN, yes. So from here we get this equals to minus or mu times N0 times dx. Yes, now it makes sense to me. So the Kerma then is going to equal to the attenuation coefficient times N0 times dx, the thickness, divided by the mass, which is the area, multiplied by the density, multiplied by this small thickness. So these two cancel out. So what do we get? We get N0 times mu over rho. Okay, and then we have this energy transfer. Yes, there is an energy transfer here. And then we have divided by area. So the Kerma basically equals to, this is the particle fluence. Remember this quantity we talked about is the particle fluence times the mass attenuation coefficient times the energy transfer. So we can write this again as N0 divided by A, and let's multiply it by the photon energy for all, and then we have here the E transfer over the photon energy. So we just added photon energies and photon energies. What do we get from here? This is basically the energy fluence. And what do we get from here? This is the energy, mass energy transfer coefficient. So if we want to calculate the Kerma of a photon beam, this means the kinetic energy released per mass. All what we need is the photon energy fluence, and we can then we multiply it by the mu transfer over rho. This is why this equation is very handy. So the Kerma is then given by the photon fluence multiplied by the mu transfer over rho, or the mass transfer coefficient. We can extend this concept again. Talk about the dose, because now with the dose, we're interested to know how much dose is actually. So this is dx. We want to know how much energy absorbed in this medium. So again, we have n photons incident on the top, and we have the area here. So we will say, okay, dn, the number that it's basically minus mu n0 dx. Okay. So this is the number, that the change, and that change is basically the number that interacted here. So the number of interactions that happened here, this minus sign is going to be plus. So the dose is then equal, this is the energy absorbed, is going to equal to the energy absorbed divided by the mass, and we will go through the same thing. So the energy absorbed equals to mu times N0 dx times energy absorbed divided by the mass, which is the area, multiplied by the density, multiplied by dx. And again, this will cancel out, and we use the trick of putting h mu divided by h mu. We will end up, this is going to equal to, again, the photon fluence, photon energy fluence, multiplied by now the mu absorption over rho. Or it's basically the photon fluence times the mu transfer over rho multiplied by 1 minus this radiation fraction. So this is again another why just to show you why these quantities are important. The energy transfer coefficient. So the linear attenuation coefficient, obviously, we use it to characterize radiation beams. However, the energy transfer, the mass transfer coefficient and mass absorption coefficients, these are used more to calculate these interesting dosimetric quantities that we will be looking into further when we in the future, inshallah. So this is my last slide today about photon interactions, about the attenuation coefficients. And I think this should conclude this section on photon interactions. And next session, inshallah, we will move towards interaction of charged particles. It's not going to be long. And then from there, we will start to really look into dosimetry deeper. So we talk about cavity theories. And then finally, we will conclude probably by looking at calibration of photon beam, measuring a dose, actually, measuring a dose for a photon beam in meat or in water. This is really our interest. Okay. Sorry for this hiccup. There should be a I0 here. I will fix this anyway. I will fix it later. So any questions?